Welcome to TMATH 124 Snow Day Applications of the Chain Rule. There are a couple of things I want us to know, and I don't want us to get behind, so I'm putting them online for you to watch. The first application of the chain rule is justifying the quotient rule. So here we're going to use the product rule and the chain rule together to verify what the derivative of a quotient is. Rather than writing my quotient as f of x divided by g of x, I'm going to write it as f of x times the multiplicative inverse of g. That takes my division and changes it into a multiplication, and we can apply the product rule. Applying the product rule here gives us p prime, the derivative of our function p. It's the derivative of the first, so that's f prime of x, times the second, that's the product of g inverse, plus the first function, f of x, times the derivative of the second function. In this case, my derivative is the derivative of g to the negative 1 of x. Here is where we're going to have to apply the chain rule because this is a composition of functions happening. Let's write out what our inside and our outside function are here. So the inside function is going to be g of x. The outside function is going to be u to the negative 1. So the reciprocal is the last thing we do. Again, I want to stress that this is a multiplicative inverse and not a function inverse. We will look at those shortly. Okay? To apply the chain rule, we have to take the derivative of each of our pieces. The derivative of u equal g of x is just going to be a u prime, otherwise known as g prime of x. And the derivative of z equal to u to the negative 1, that's a power rule. We bring the exponent down in front. It gives us negative 1 u to the 1 less power. Minus 1 is negative 2. Now that we have these components, the chain rule says we multiply these two derivatives together, and we will have the derivative of our composition. So returning back to, so there we go. So we've multiplied them together. We've written that the derivative of g inverse of x is the derivative of g times negative 1 u to the negative 2. Rewriting u in terms of g of x gives us negative g prime of x in the numerator over u squared in the denominator, and that u squared finally becomes a g of x, the quantity squared. We can now take this as our derivative for g inverse and see where that gets us. All right, so simplifying as we go from our first take at the derivative, I'm going to just write this in the denominator. Since it's g to the negative 1, we know that's just 1 over g of x. So our first term becomes f prime of x over g of x plus f of x. And we now have what the derivative of g to the negative 1 is. It's negative g prime of x over g of x squared. The last piece is to realize that we need a lowest common denominator to add these two terms together. That's going to be g squared. So you will need to multiply the first term by g of x over g of x to get to that denominator, making the first term f prime of x times g of x. The second term is now minus f of x times g prime of x, and this whole thing is divided by g of x squared. So that is our quotient rule. as you have learned to love it. If you read what the next question asks, we actually did this yesterday. It asked us to find the derivative of the natural log of x by differentiating the identity e to the natural log of x equals x. Well, we did that. I hope you remember that the derivative of natural log of x is in fact 1 over x. But let's take it a step further. What's special here is that e to the x and natural log of x are inverse functions. We can do this same type of differentiation with any set of inverse functions. What are inverse functions, you might ask? Well, that's any function that undoes the other function. Examples might be x squared and the square root of x, sine x and the arcsine of x, e to the x and natural log of x. Those are all examples of inverse functions. More importantly, what you need to recall about a function and its inverse is that it satisfies this beautiful composition identity that f composed with f inverse of x always equals x. So whatever f inverse does to x, f will undo it. And in fact, you could do it in the other order. You could say that f inverse of f of x also equals x. So starting with this identity of functional inverses, we can differentiate both sides and find how the derivative of f inverse relates to the derivative of f. And that's what we're going to do. All right. This is section 3.6 actually. So let's take the derivative of f composed with f inverse of x. We're going to need a chain rule on the left-hand side. The inside function is going to be f inverse. The outside function is going to be f. So I set u, the inside function, equal to f inverse of x, and I set the outside function, let me just call it z, equal to f of u. We have to take the derivatives. So the derivative of u is going to be what we're looking for, the derivative of the inverse of f. And the derivative of z, well, that's just f prime evaluated at u. So now we are ready to write out what the derivative of the left-hand side should be. So it's the product u prime times z prime, which we can write in terms of the derivative of f evaluated at u times the derivative of f inverse evaluated at x, which, we're down here, can be written as f prime evaluated at f inverse of x times f inverse of x prime. So I skipped ahead here. I want to take the derivative of both sides of this identity. When we do that, the right-hand side, the derivative of x with respect to x, is the easiest thing here. That's just 1. And on the left-hand side, it's what we computed earlier. Okay, that looks like a bloody mess, but that's all right, because what we're really interested in finding is the derivative of f inverse of x. So that's what we want to solve for, and we're going to do that by dividing both sides by this factor, f prime of f inverse of x. So we get that the derivative of f inverse is 1 over the derivative of f evaluated at f inverse of x. That may not sound too too clear, but let me give you a couple of examples to see what I mean. Okay, so let's pick your favorite inverse function. Today, my favorite inverse function is going to be the arcsine of x. So this is the function that undoes sine, and the way you can think about it is it's the angle whose sine gives you an output of x. So I can ask, what's the derivative of arcsine of x? According to what we just computed, it's going to be 1 over the derivative of sine, that's cosine, evaluated at the arcsine of x. Maybe that doesn't look too exciting, but remember what arc cosine represents. Arc cosine is the angle whose sine gives you an answer of x. So let's draw a little right triangle over here with an angle theta, and let's label the lengths of our triangle so that the sine is x. Well, that means our opposite edge has to have a length of x, and our hypotenuse can have a length of 1. Then the sine, which is opposite over hypotenuse, is x over 1, or x. It's a perfectly lovely right triangle. You can use the Pythagorean Theorem to find the adjacent side. That's going to be the square root of 1 minus x squared. And then this is asking for the cosine of that angle. And the cosine is adjacent over hypotenuse. We know what the adjacent side is now. That tells us that the derivative of the arc cosine of x is 1 over the square root of 1 minus x squared.